Okay, so we're going to talk about, the first thing is wave propagation. What I mean by wave propagation is how does sound move around through a space, okay? Because that's what it does. How does it propagate in space? Well, the first thing you need to know about how it propagates in space is that it does so at a predictable rate. So we sort of know how fast it moves. On average, it's about 1,130 feet per second. That's a bit of a moving target, though, because that is affected by other things, like the temperature can affect how fast sound moves. Sound moves faster in warm air than it does in cool air. So as the temperature increases, so does the speed of sound. Humidity can affect it. Altitude, which changes pressure in the air, can affect it. So it's not that 1,130 feet per second is not like a hard fixed thing. In fact, here in North Carolina at this altitude, I've conducted measurements from time to time, and it's actually about 1,050 feet per second here in Winston-Salem, North Carolina. But in other places it would be closer to 1,130. Other places it might be a little bit faster than that. But it's pretty close to about 1,000 feet per second-ish, right? And we can, using 1,000 feet per second, which is a nice, easy, round number, we can do a lot of really simple calculations just in our head, figuring out like what's going to happen with sound, and it's close enough. You're just saying it's 1,000 feet per second. That's close enough to get decent results. We're going to deal primarily in feet per second because it makes the math a little bit easier, because it works out to where it's about 1 foot per millisecond, and so when we start like working out time and stuff, the math is easier to do actually in feet per second. But if you translate this out, it's about 344 meters per second. But we're not going to spend a whole lot of time working in metric, not because I have anything against metric. I think metric's fine, but I just find the math that we're going to do is a little bit easier to do if we do it in feet. What's really happening is you're pushing on those little molecules, and then they push on the ones next to them, that push on the ones next to them, that push on the ones next to them. And eventually they'll push against ones that are next to your ear, and your ear will move. Okay, the little bones inside of your ear will move. Okay, this is what sound is doing. So, and that's called a longitudinal wave, where the direction of the motion is actually the same as the direction that the energy propagates. Yes. Okay, the slinky is another way of looking at that. And if if we get some time a little bit later, maybe next week, I'll show you that. So that's what's going on here. Now, the thing you need to understand is very often we will draw sound and look at sound as though it's a transverse wave. So we'll draw it like this, on the board, because that's a little bit easier for us to analyze. But that's not what sound is doing. Okay? Let me show you how that propagates, or what's really happening when we draw it as a transverse wave. So here again, here's all of the air molecules in the room. We're just going to look at a few of them. We're going to go through. And so there's this thing called compression. And the compression is when the air molecules squeeze together. Okay? And then there's the thing called the rarefaction. The rarefaction is where the air molecules spread apart. Okay? So they're compressing or they're rarefacting. Okay? And they're really doing both at the same time. And that's the wave. Okay? So it's pushing and pulling on your ear. Now what happens is we can draw that as a graph of air pressure. Okay, so when we're in a compression, that's high pressure, right? We're putting a lot of pressure on those air molecules. When it's a rarefaction, that's low pressure because we're spreading them out. And we draw that as this transverse wave, and when we go up, that means compression because air pressure has increased. And when we draw the line down, that means rarefaction because the air pressure has decreased. Okay, so this line that goes up and down is not a line of what is happening in physical space with the sound. The sound is not moving up and down and up and down. I have had people really misunderstand this. I have had salespeople that have tried to sell me equipment that have told me that that's what's happening. Like I've had people tell me, oh, you have to be really careful where you put the subwoofer in the room because if you put it in the wrong place, those wavelengths are so big that that sound can go right over your head if you get it in the wrong place. It's like, no, that's not exactly how that works. You can't actually hide from a longitudinal wave. Yes, Kai.
So I'm not sure if this is just the diagram stuff, but the compression and rarefaction are the length of, like if you were to measure the compression and rarefaction areas in the actual air, like that was
there's an actual distance that is.
I know, but would they be equal, or is the fact that the compression is squishing them together and rarefaction is?
It depends on the wave.
Okay.
If it's a sine wave, yeah, they're the same,
Okay.
but doesn't necessarily. In a complex wave, they wouldn't be.
Okay, cool. I was just wondering for the fact of like the sine wave is a consistent thing, but it looks like the refraction and compression areas are different. I'm not sure if that's just a visual thing that's throwing me off. Or
Yeah, it's just. I mean, this is why we don't do diagrams of longitudinal waves because they're a little bit harder to capture in a visual format. This was the best thing we could come up with when we were working on the book. Like, got to figure out a way to visualize this, and this was the best we could come up with. But it's a very difficult thing to visualize. It's much easier to visualize this line that we draw up and down, but you can get confused by that because you can think that that's what sound is doing. It's not doing that. It's not moving up and down. It is pushing and pulling at you.
I just wanted to make sure there wasn't some like breakdown of how the actual compression refraction areas are different. Like they aren't equal. Like I always thought it was like, oh, it would refract by the same amount that it would compress.
Yeah, it's not, I get what you're saying.
I'm not sure if that. I think it's just a visual.
Yeah, it is. We just drew it like this because you can it makes it easier for you to see where it's coming in there.
Gotcha. Just making sure.
I have a question.
Yes.
Can you just back up to the two names of these waves?
Transverse and longitudinal.
Okay, so this is transverse.
Yep.
And why is it's called that? Because the movement is not the same as the direction.
Yeah.
And then the other one is longitudinal because it actually.
Yeah.
And so is this real? That's like a weird question.
What?
It's like, so why does this one exist?
Well, there are things that do move up and down, like water waves actually move up and down, right? No, but radio waves go up and down, right? So that actually happens. So there are, because it's doing magnetic poles. but it's I think that's how it works anyway. But for the most part, the things that we are interested in are longitudinal waves, because that's what sound does.
Okay.
Right? Now, if you think about so think about something like if we now take sound and turn it into audio, and now it's voltage on a wire, right? And you try to measure that with a meter, well, that voltage is going to be increasing and decreasing, right? Increasing and decreasing. And the only way to really graph that is going to be a transverse wave, because it's a value that's going up and down, and you would just, you would graph that, and it would be this transverse wave. Okay. But that also does not mean that that electronic energy is moving up and down inside of the wire. It's just voltage is increasing, voltage is decreasing, voltage is right?
So then, so is the only reason that this diagram exists, the transverse wave, is because the longitudinal wave is more difficult to?
For our purposes, yes.
Okay.
Yeah. But the transverse wave exists because it's easier to diagram.
Okay, and that's okay.
That's really it. But it is an abstraction of something else, right? So we are using this transverse wave as an abstraction for something that is difficult for us to visualize. But when you start seeing this line that goes up and down, you got to think of it as a graph, not a picture. Okay, it's not a picture of a wave. It is a graph of air pressure amplitude.
So like if it's drawn like where they're really close together,
yeah,
it's just representing.
Yeah, it's representing pressure. Yep, exactly. Here's another way of looking at it. So this would be like an actual example of how we could translate a longitudinal wave into a transverse wave. So if we just had like a spring that had a weight on the bottom of it, and we let it kind of bounce, but had like a piece of paper that was like moving behind it with a pencil on the weight. So there's a little pencil on there that would draw on the paper as it moved up and down, and if you like moved the paper along there, it would draw a little picture, right? And the picture represents the position of the weight at any given point in time. But this graph is not showing you what the slinky was doing.
Yeah.
Okay. Right? This thing that's going up and down is not the same as the slinky squishing together and spreading apart, but it is abstracting that motion of pushing the slinky together and pulling the slinky apart. It's converting that to a graph that shows you that, when the line goes up to the top, that means the slinky was close together. When the line goes to the bottom, that means the slinky was stretched far apart. Yeah.
So is compression happening anytime the wave is positive relative to its x-axis, or when the slope is positive?
Say that again?
The compression, is it happening when the wave on the x-axis, when it's above the axis and it's making N shape versus U shape?
So
or is it any time the slope of the wave is positive?
Yeah. So if we're not going to be pushing and pulling on the air, that's sort of like the static state of the air, right? The air molecules, they have their place where they live normally, okay? Anytime you start squishing them together at all, that's a compression, okay? And anytime you stretch them apart from their normal state, that would be a rarefaction. The extent to which you compress them or stretch them out, that's just amplitude. But any of this whole area that is above that zero is a compression.
Okay, great.
Yeah, Laura.
What do you hear when you what do you hear?
Well, so good. So that's the next thing, right? So what you hear nothing if all it does is compress, right? And never refract, right? What we hear we don't hear anything until that happens over a period of time. Okay, it has to happen multiple times over a period before we actually we're able to turn that into something we hear. Okay, so what happens is that air pressure is pushing and pulling on our eardrum, right? And as our eardrum moves, there's little bones that move, and that causes a vibration inside of our cochlea, and that vibration that excites the little fluid inside of your cochlea, and the little fluid inside your cochlea will, depending on how it's dancing around, will resonate or be very sympathetic to a little hair inside of your cochlea that is a certain length. And there's lots of little hairs inside of your cochlea that are lots of little lengths. And the longer they are, or the shorter they are, determines like which sorts of excitement that they'll respond to. And so when the little fluid inside your cochlea is vibrating at a rate that is sympathetic to one of those hairs, that hair starts wiggling. And when that hair starts wiggling, it sends a little electrical impulse to your brain. And your brain knows that when it hears the impulse from that particular hair inside your cochlea, then that sounds like this. And when it hears this little hair moving, that sounds like this. And in reality, a lot of them, when you get real sound, like when you're hearing my voice right now, my voice is making lots of little hairs inside your cochlea move all at the same time. And so your brain is putting that together. It's hearing all of those little individual tones, and it's mashing them together into this thing that sounds like Jason. Okay? So it has to happen, but it has to happen over and over again, right? So you have to have this compression, refraction over and over and over again to create an actual sound, and that's called hertz, cycles per second. How many times does it compress or refract every second? So if it only does it once in a second, that's not fast enough for us to turn that into sound. Okay? It has to do it at least 20 times in a second in order for most people to have anything at all happen inside their ear.
So
okay?
hertz is the cycles of compression and refraction
Yep.
per second?
Exactly.
Okay.
Okay? So the number of times it compresses and refracts every second, that's hertz. Okay? And it has to do, generally, on average, at least 20 full cycles in a second before we'll even hear anything. And even that is hard to hear for most people. 20, it usually has to be at least 40 or 50 for most people to actually say, okay, I hear the sub-bass.
And so, sorry, can we just so I get it's the cycles of compression and refraction per second.
Yep.
But what is if I were to explain that to somebody who doesn't know what compression and how do you say that in
well,
what does that mean is actually
it's the pitch.
happening?
It's the pitch.
Okay.
So a low hertz, right? A low number of cycles per second would be a lower pitch.
So a lower.
Right? Yeah. So low frequency,
Okay.
less cycles per second. High frequency, more cycles per second. Right?
Okay, so it's just the pitch that
Yeah.
you hear it at?
Yeah.
Okay.
And so Kai, sorry, you had a question.
Oh, I was just going to say, so a 1 hertz wavelength would be 1,130 feet long then? That's how fast it's moving in a second. And it's
Yeah.
1 cycles. So that, okay.
Yeah.
So
That would be a lot, right?
yes. That's
So yes, on average, most, if you go out and people have done this, they go and survey, lots of people, and they play lots of different frequencies in their ears, and they tell me when you hear something, and it averages out to be most, somewhere between 20 hertz and 20,000 hertz. That's kind of the average range of human hearing. That being said, there are people that can hear beyond 20,000 hertz. There are people who can't hear all the way to 20,000 hertz. I can't. I think the highest I've ever really been able to perceive something is more like 18,000. I have a hard time hearing much beyond that. I don't know that I've ever heard 20 hertz. I've tried, but it just that's tough to hear. I feel like I've felt it before, but I'm not sure I could say I've heard it. To make 20 hertz at any amount of amplitude, it becomes this thing that's big enough to actually physically move your body, and you feel it vibrating your body more than you feel it vibrating your ear, and so that's just kind of a very bizarre phenomenon. So I can't say for sure that I've ever heard it, but I'm pretty sure I've felt it before.
So what's the difference between pitch and volume? I know that sounds like a stupid question, but
So pitch is hertz. Pitch is cycles per second. How many compressions and refractions happen every second? And that's high pitch, low pitch, right?
Okay.
Loudness is all about amplitude. So that's to what extent was it compressed and to what extent was it refracted? Was it compressed just a little bit and refracted just a little bit? That would be low volume. If it was compressed a lot and refracted a lot, that would be a high volume. Okay. So if the more, think about it this way, higher compression means it's pushing harder on your eardrum.
Okay.
And therefore your eardrum moves more. And that sounds louder to you.
Okay.
Eardrum moving a long ways sounds louder than eardrum moving a little way. right? So it's called amplitude. So how high was the pressure?
So something, a sound can be compressing and refracting a whole lot.
Yeah.
But if the amplitude isn't
Yeah.
high enough, it doesn't actually
You don't hear it, yeah.
register as anything.
Yeah.
Okay.
Yep. So we'll get into amplitude more in a couple of weeks, but
I feel like I just need
for
to
the
understand.
physics nuts out there, you know, the smallest amount of pressure that actually turns into anything that average people can hear is 20 micropascals. Okay, so you have to have at least 20 micropascals worth of pressure in order for your eardrum to move.
Okay.
Okay, and that's like, you know, a mosquito flapping its wings. So it's like
Yeah, I
you
just
can't.
feel
It's
like-
I'm not even sure I would hear that. You know.
I feel like I needed to understand like the true differentiation between
Yeah.
those things so I can understand what's happening.
Yeah.
That's the only thing.
So yes, one cycle is one full compression, one full refraction. You might also hear some people use the word period, the period of the wave. The period of the wave is the amount of time it takes to do one full compression and one full refraction. So how much time does it take to do one cycle? That's called the period. We don't deal in period a whole lot in the kind of stuff we'll do. But we will deal in frequency quite a bit. Cycles per second. How many times does it compress and refract in 1 second?
What is an application of period? Because isn't it just basically double frequency and then put into seconds? Or like what's an application? Well, or is it just outside of sound? It might be
It's
something.
just not something we deal with a whole lot. It's not a variable that's particularly important to us. Wavelength is pretty important to us. So we're less interested. So wavelength would be how far did it move in distance to do that one cycle. That's important to us. But the amount of time it takes to do that one cycle is less important to us. Okay, we don't run into that too much. So let's talk about wavelength. So now, if we take this idea now of the wave, right, that is, remember, a longitudinal wave that is actually compression and refraction of air molecules in a physical space, you could measure the distance between the compressions, and that would be a wavelength. That would be the actual distance of a full cycle. And that's called the wavelength, the distance the sound travels in order to complete one cycle. Now, the wavelength is dependent on two variables. There are these three variables that are interconnected. It is speed of sound, frequency, and wavelength. If one changes, the other two change. Okay? The wavelength is equal to the speed of sound divided by the frequency. That'll give you the wavelength. Consequently, if you needed to know the frequency, you could take the speed of sound and divide it by the wavelength, and you'd get the frequency. If you wanted to know the speed of sound, you could multiply the wavelength and the frequency, and you get the speed of sound. Okay? So when I say I've done measurements of the speed of sound, that's what I've done. So this is the math that we're going to do for the next day or two, is just very simple operations between speed of sound, wavelength, and frequency. Very simple math. This is not hard. Okay? I've drawn this little triangle again for the math impaired like me. This helps me. So with this is the represents the mathematical relationship of these three variables. So what you do is, if you want to know something, so if I want to know wavelength, for example, I circle that. That's going to be my answer. And in order to find that out, I have to manipulate these two variables. And right now, speed of sound, or C, is on top of frequency, which tells me I have to divide those. It's a fraction now. So I take speed of sound divided by frequency, and I will get wavelength.
Is this a thing that people do? I've never seen it. Or did you make this up?
I didn't make it up, but so presumably I've seen other people do this. I don't know how popular it is, but it makes a heck of a lot of sense to me. So I like
I've
this.
never seen that before.
If I want to, excuse me, if I want to know frequency, I'm left with speed of sound on top of wavelength. So I take speed of sound divided by wavelength, and I will get frequency, right? If I want to know speed of sound, the two variables left are wavelength and frequency, which are right next to each other, and that's multiplying, right?
Huh.
Okay. So this helps me. If it helps you, you can use that too. But if you like algebra, I should be able to just give you wavelength equals speed of sound divided by frequency, and you should be able to convert that into the other three formats of that. Okay. But I don't always think that way, so it's easier for me to remember something, a picture, than it is for me to remember a formula that is a little too abstract for me. Okay. So let's try this, shall we? No calculators. What is the wavelength of 20 hertz?
50 feet.
Why is it 50 feet?
Because it's 1,000 divided by 20.
Yeah, so we want to know wavelength, right? And to get wavelength, we have to do speed of sound divided by frequency. What is the speed of sound?
Roughly 1,000 feet per second.
1,000 feet per second, right? If we're going to futz around with math in our head, it's easier to deal with 1,000 than 1,130. So we'll just sort of say it's 1,000. If we're doing it in our head, speed of sound is 1,000 feet per second. So 1,000 feet per second divided by the frequency, and the frequency is 20, right? 20 hertz. So 1,000 divided by 20, hopefully you can do that in your head. 1,000 divided by 10 would be 100, right? 1,000 divided by 20 would be 50. So 50 feet is the wavelength of 20 hertz. You okay?
I can't do that stuff in my head. It's
Okay.
really that bad, but it's fine. It'll be okay.
You'll get there. Okay, so there's one of them. Clear ink. Excellent. Okay. Here's another one. What is the frequency of a sound that has a 10-foot wavelength? Okay, so I want to know frequency. To get frequency, I have to take speed of sound divided by wavelength, right? So speed of sound, 1,000 feet per second, divided by 10, right? 10-foot wavelength. 1,000 divided by 10. Right. You get 10 100s in 1,000, right? So 1,000 divided by 10 is 100 hertz. Okay? So if you see a sound that has a 10-foot wavelength, it's probably going to be somewhere around 100 hertz. Oops, clear ink. Here's another one we can do in our head. What is the wavelength of 1 kilohertz? Now, when I say kilohertz, what do I mean? Thousands of hertz, right? So 1 kilohertz would actually be 1,000 hertz. You could write it like that. But when you get into things like 18,353 hertz, it's easier to just write that as 18.5K or something, right? So if you ever see kilohertz, just know that there's 3 zeros on there that you can't see, okay? So wavelength of 1,000 hertz. Well, to get wavelength, I have to take speed of sound divided by frequency. So speed of sound is 1,000 feet per second divided by 1,000 hertz. What is 1,000 divided by 1,000? Taylor? 1, right? See, we can do this in our head. 1 foot. Wavelength of 1 kilohertz is 1 foot. That big.
So I'm a little confused on. That was just all a little fast for me.
We're going to do hundreds of these.
Okay, so I'm not sure, I'm not even sure, how to read the problem yet, how to know. So we always know that
So I'm asking for wavelength, right? What is the wavelength?
Okay.
So the answer is, I need an answer in wavelength,
Okay.
right? That means wavelength.
Okay.
So that's the answer I'm looking for,
Okay.
right? So if that's what I'm looking for, then I know I have to work with the other 2 variables,
Okay.
speed of sound and frequency.
And C is speed of sound, which is always 1,000. Okay.
Yep.
Okay.
But we're going to do a whole bunch of these.
Okay.
Here's another one. We should be able to do this one in our head. What is the wavelength of 250 hertz? Okay, So wavelength, I'll write it out this way. Wavelength equals speed of sound divided by frequency, right? So speed of sound, in this case, wavelength is going to equal speed of sound, which is 1,000, divided by the frequency, which is 250 hertz, right? So what is 1,000 divided by 250? How many 250s make 1,000? It's 4, right? So 1,000 divided by 2 would be 500. 1,000 divided by 4 would be 250. Or 1,000 divided by 250 would be 4. So this is 4 feet. 1,000 divided by 250 is 4 feet. That's 4-foot wavelength. That's the sound we hear all the time, 250 hertz. You're hearing a little bit of 250 hertz in my voice right now.
Is there a reason why lambda is the symbol we use for wavelength?
I don't know.
Okay.
Somebody with a white lab coat decided that one day.
We have all of these. So each one of them had different branches.
I refer those kind of issues to people much smarter than me. I actually had somebody try to fight with me last year about the variable I was using for speed of sound, but
Brian?
probably Brian, but I won. I was right. I made him look it up, and he's like, "Oh yeah, you're right." It's like, okay, thank you. Okay, so frequency of a 5-foot wavelength. Well, frequency equals, right, speed of sound divided by wavelength. So in this case, it's frequency equals 1,000 divided by 5. What number could you have 5 of that would make 1,000? 200, right? So 200 times 5 would get you 1,000. So this would be 200 hertz. There you go. Oops. Okay, here's a tricky one. This one's not on our triangle. Let's see if we can do it. What is the frequency of a sound that takes 50 milliseconds to complete one cycle? Well, let's think about it for a second. We don't know how to deal with milliseconds yet, do we?
No.
I haven't taught you that. But I have told you a way that you could figure that out. So we know that sound travels 1,000 feet per second, right? And therefore, how many milliseconds are in 1 second? 1,000. 1,000 milliseconds in 1 second. So it's 1,000 feet per second, or 1 foot per millisecond, right? 1,000 feet in a second, 1,000 milliseconds in a second. That would be 1 foot for every millisecond. Okay? So if we know that in sound world, 1 foot equals 1 millisecond-ish, again, depending on temperature and pressure and altitude and humidity and all those kind of things, then we would know that if something is taking 50 milliseconds to complete one cycle, then it's traveling how many feet to do that? So 50 milliseconds is going to equal 50 feet, right? Well, there's our wavelength. 50-foot wavelength. Now we have a variable we can work with, because wavelength is in our triangle here. So I want to know what frequency that is. I know the wavelength. Frequency is equal to speed of sound divided by the wavelength, which is 50 feet. 1,000 divided by 50 equals 20. 20 hertz. Yeah. Interesting enough, that was the first problem we did, if you remember back from 10 minutes ago. Okay. So we actually did that one in our head, even though I said do it in a calculator. Should we do it with a calculator now, just to further drive this home? When we do things with a calculator, we should be slightly more specific about our speed of sound because we can, right? The calculator will do some of the thinking for us. So when we're doing speed of sound with a calculator, what number should we use?
1130.
Yeah, 1,130. So here's my calculator. So if it's 1,130 feet per second, then what is our feet per millisecond sort of deal go there? So how did we get it before? We did 1,000 divided by 1,000 basically, right? 1,000 feet per second divided by 1,000 milliseconds, and we got 1. 1,000 divided by 1,000 is 1. So if we did that same math again, just using that new number, it would be 1,130 feet per second, right? Divided by 1,000 milliseconds, right? And we get 1.13. So it's 1.13 feet per millisecond. Just write that down and memorize that. Okay? I mean, you can figure it out later on your own if you want to, but if you just memorize it, then you don't have to later. So sound travels 1.13 feet per millisecond. So you're going to commit that to memory, or you're just going to stick it in your calculator's memory and tell your calculator to remember it for you. So that's what I did. So now I know that, and I have this sound that takes 50 milliseconds to complete a cycle. And so 50 milliseconds. And I know that sound travels 1.13 feet per millisecond. So I'm just going to take that 50 times my 1.13. And I get 56.5. So that's 56.5 feet, right? So if sound is traveling 50 milliseconds to complete one cycle, it traveled 56.5 feet while it did that, because it's 1.13 feet for every millisecond. Okay, so I'll have my calculator remember that. And now I can say, okay, I want to know the frequency now, which is speed of sound divided by the wavelength. So speed of sound is 1,130 divided by my wavelength of 56.5 equals 20 hertz. Okay? Another one with calculator. What is the wavelength of 20 kilohertz? Well, what's the formula to figure out a wavelength? Wavelength equals speed of sound divided by frequency. What's speed of sound? 1,130 divided by frequency. What's our frequency? 20,000, right? Not 20, 20,000, because I said 20 kilohertz. So 20 with 3 more zeros for 4 zeros total. Okay? And we get 0.0565. What does that number mean? 0.0565 of what? Feet, right? So it's 0.0565 feet. That's very, very small. Okay. There you go. Let's try another one. Frequency of a 7-foot wavelength. How do I figure out frequency? Yep. So what would speed of sound be? 1,130 feet per second divided by the wavelength, which is 7, right? So divided by 7, 161.43. What does that number mean? We're in hertz. It's hertz. It's frequency. 161.43 hertz. There's your answer. 7-foot wavelength is 161.5 hertz-ish. Okay, let's try another one. What is the wavelength of 3 kilohertz? How do I figure out wavelength? speed of sound divided by frequency, right? So speed of sound is 1,130 feet per second divided by the frequency, which is what? What number do I put in here? For 3 kilohertz, that would be 3,000, right? Not just 3, 3,000. The K means something. So 3,000. So 3 with 3 zeros on it. And we get 0.376, or we could just call that 0.38. 0.38 feet, right? Wavelength, 0.38 feet. What is the wavelength of 300 hertz? Let's see if you're right. That would be speed of sound, 1,130 feet per second, divided by 300. What did you say?
3.76.
Yeah, that's what I got too. Okay, anybody else get that? Somebody try it. So here's my rule. This is the simple math. It's going to get harder, but nobody has the right answer until 2 other people have that same answer. That includes me. So even if I do it on the board, it's not right until 2 of you got the same answer. Okay? So did we have 2 other people who got that? Okay, good. Then it must be right. It's unlikely that all 3 of us would make the same mistake. Yeah. What is the frequency of a 3-inch wavelength? Oh, crap. We don't know how to do this in inches, do we? Let's think about that for a minute. We don't know how to do it in inches, so we either have to figure out how many inches per second is the speed of sound, which would be a lot of inches, right? It would be 1,130 feet per second times 12, so it would be, what, something like 13,000 something, okay? That would be a lot. That's a big number. I don't like big numbers. So it'd be easier if I could just figure out how to convert 3 inches into feet. Okay, well, how many inches are in a foot? 12 inches in a foot, right? So I could figure out how many feet is an inch, right? I could say, by saying 1 foot divided by 12 inches, because there's 12 inches in a foot. So 1 foot divided by 12 gets me 0.083 feet. So 1 inch equals 0.083 feet. And I have 3 of those inches, right? So I can take my 0.083 and say times 3, because I have 3 of those, and I get 0.25. So 3 inches equals 0.25 feet. That's something you probably could do in your head too if you realized that, well, there's 12 inches in a foot. I have 3 of them. 3 times 4 is 12. So it's a quarter of a foot. 3 inches is a quarter of a foot, 0.25 feet, right? So you could figure that out in your head if you wanted to, but you can also sort it out without too much trouble with the calculator. So we've now shown that 3 inches is 0.25 feet. That's our wavelength. That's a wavelength that we can work with because it's in feet. So I'll just say, remember that in case I forget it in a moment. And to get frequency, I need 1,130 feet per second divided by the wavelength, and I'll get frequency. So 1,130 divided by 0.25, and I get 4,520 hertz. Or I could also call that 4.52 kilohertz. If I just to convert hertz into kilohertz, just take that little decimal place and move it 3 times to the left, and you'll get, now you'll have kilohertz. Okay. So either answer would be right. You could say 4,520 hertz, or you could say 4.52 kilohertz. Same thing. Okay, I got another one here. I got 5 more minutes. We can keep doing this. I can do this all day. What is the frequency of a sound that takes 3 milliseconds to complete a cycle? All right, we've done this one before, right? First, we have to convert that milliseconds into feet. right? So when we're using a calculator, how many feet per millisecond do we have? Anybody write that down? I told you to memorize it.
1.13.
Yeah, 1.13, 1.13. So just memorize that. Then you don't have to look it up because we're going to use that number a lot. Okay. So 1.13 feet per millisecond. I have 3 of those milliseconds. So it's going to be 1.13. What am I going to do with that? Times 3, exactly. And I get 3.39 feet. That's my wavelength now. Okay. So calculator, please remember that for me. And I will now say speed of sound, which is 1,130 feet per second, divided by that thing I told you to remember, which was 3.39. And I get 333.33 of what? Hertz. Exactly. That's it. That's all I got today. We'll do resonance on Monday. How are we doing? We don't have class on Monday. Friday. We'll do that Friday. So what I'm going to do is I'm about to sit down and I'm going to email you a little file that will have a whole bunch of questions just like that, plus some other ones. So you can start working on that now. Start practicing these and see if you can figure it out. If you have trouble, let me know. You can go back and look at the video that I'm about to also upload to YouTube, and you can watch this whole thing again. You can take this whole class all over again. What's that? Yes, as many times as you want. Work on those. If you get to ones that you don't know how to do, that means I haven't taught you how to do them yet. So don't worry about that. Don't do those yet. Okay?
No class Monday.
Yeah, no class Monday because it's Martin Luther King Day. So no class. You could
Do your homework.
you could do this math, right? You could do it all day. There's plenty of questions in there. Okay, so yeah, if you get to ones you don't know how to do, don't stress. Just don't do them. If you feel like you totally got this and you're ready to move on, you could read ahead or something and learn about resonance and figure out how to calculate that. But you're fine to wait till next Friday. Okay, any questions in the last 2 minutes that I have? No? Okay, so this is how class is going to work. We're going to come to class. I'm going to tell you something for a few minutes, and then we're going to do math. Okay? We'll do this every day, all semester. Okay? Okay, that's it. We're done. Thanks.